thought I would start this by making sure that I answer Anna's questions, so that we know that that is done. So, what feature are you mapping and why are you mapping it? So we are mapping ice-wedge polygons that develop on point bars. We are interested in the co-evolution of polygons and meanders. That said, please keep in mind that I know a little bit about meandering and fluvial systems in general. I don't know a lot, to say the least, about permafrost and ice-wedge polygons. So I'm trying to catch up and stuff, but I still need to learn more. What imagery do you use? So I don't have access to high-resolution imagery, and we definitely need high resolution for this kind of work. So see this as more of a proof of concept. This is, I'm not sure this qualifies as big data at this point. I think it doesn't, but I'm basically using some S3 base layer available through QGIS, and I save that as a georeferenced image and then put the results back into QGIS when I'm done in Python. What technique we are using? We are using semantic segmentation using a Unet-type convolutional neural net. And very importantly, we are doing a lot of post-processing to get to, not to the polygons themselves, but to a graph representation of the polygons, and you will see that later. I just use my laptop at this point. What is holding you back to map it across the Arctic? So what the setup I have right now, this is not, it's not working in the cloud. I need to download data. I don't have access to proper data at this point. And also this is kind of a side project. We don't have funding specific to this, but these things are so beautiful that I couldn't stop working on them once I saw them. So a bit about my background. In the last few years, our group did quite a bit of work on using remote sensing data, mostly Landsat, to better understand the migration of meandering rivers, and not just that, but also what kind of deposits they are leaving behind. So here, what you see on the left is a color-coded map through about 30 years of the types of deposits that are left behind when a beautiful meandering river, this is the Mamore in Bolivia, keeps migrating, and the colors are basically, let's keep it short, there are different types of deposits, different types of point bars as a function of curvature and migration rate along the river. So this is the kind of work I'm doing a lot. And I also spend a lot of time just looking around in Google Maps and Apple Maps for beautiful meanders. And so these screenshots are from a time when Twitter was a better place, and there was a lot of good interaction going on. And I posted this image on the left first, I think, and I called it pattern ground, which I think is the wrong term for this actually. So that reflects my expertise on permafrost. But both Dan and Robert were very interested, and we messaged each other and said, let's meet on Zoom and talk about this stuff. So that's how the project started. And we quickly ended up, certainly I was most fascinated by a few spots in Siberia. So here's the Lena Delta, and one area that is basically my favorite, there are a few highlighted here with the red boxes. The Yana Delta is beautiful and full of polygons, but there is this small river called the Diagarin River, which shows some of the most interesting patterns. So I'm gonna talk mostly about that for the rest of this talk. So let's zoom in. Here is the river. I'm mostly looking at this branch coming like this and then entering the Laptev Sea. And if you zoom in further, this is what struck us as really interesting. So obviously you see some meanders here, and then usually, as you could see in that Landsat animation, what you see in the morphology and in the patterns of the vegetation on the top of the point bar, you see these scroll lines which are running parallel to the paleo channel, right? But you don't see the lines that are perpendicular to those scroll lines. And here that is different. This is a unique situation where these, we call them radial lines, but they are beautifully preserved. And the hypothesis, our hypothesis is, to kind of jump ahead a little bit, is the reason that you see these polygons forming this way and preserving the history of meandering this way. The reason for that is that there is these rivers are migrating slowly enough, which means very slow, but consistently, so that you always have a narrow strip of freshly formed land, and that has just enough time to be populated by ice wedge polygons. If the river was migrating much faster, this wouldn't be possible, this kind of pattern formation. And if you go to other places like in the Yana Delta, things are a little bit messier, still beautiful patterns, fairly regular, but this idea that the speed of migration controls the patterns, I think is fairly, well, maybe not obvious, but there are hints here that that's what's going on. If you look at this bar over here, you see how it's kind of, it's very rectangular pattern here, and then it becomes more isotropic, like, you know, hexagonal and pentagonal here. And I think the reason for that is that the rate of migration here is too fast compared to over there. And that's what is reflected in the patterns. And this is interesting, of course, for a number of reasons. Obviously, we are, you know, at a time when things are melting in general, things that are frozen, and also there is a question how rivers respond to the warming that is going on. And this is a recent paper where they looked at some rivers in Alaska, and here is the Kobuk River, which is migrating pretty fast. So this is like maybe 200, 150 meters in 30 years. And they are basically saying that they are slowing down because the vegetation is encroaching onto the point bars as the permafrost is retreating. I think that's the main idea of this paper. So if we look at this Kobuk River for a second, I can elaborate a little bit more about this idea of speed of migration and new land formation versus the speed of ice wedge polygon formation. So here we basically see an old floodplain on the left, and then this is a young point bar. So remember, this river is moving like, you know, at least a few meters per year, if not more, pretty dynamic. And if we zoom into this area a lot, you can see that the old floodplain has a bunch of ice wedge polygons. The young point bar has nothing, as far as I can tell. And probably the reason for that is that this is moving too fast. So through time, you know, if things were not melting right now, this could develop, obviously, ice wedge polygons here as well, but those wouldn't reflect so nicely the you know, the structure of the point bar as we see in the Siberian examples. So a few words about the methodology that we are using. The primary tool here is a Unet, which roughly looks like this. This is from the original paper, not going to go into details here. And then we use patch-based segmentation. So in the middle, you see the label from the training data. Here is the image patch. And there is the blending on the right side. So we do some data augmentation as well to, you know, increase the number of training patches. And then to eliminate edge effects when you do the prediction on large images, to eliminate those edge effects, we use the methodology described in this paper, which uses hand windows to eliminate these patches, basically some spatial weighting. And then here are some training and validation loss and accuracy curves. In general, I think it looks pretty good. The validation loss just keeps, creeping up as you keep training. You don't see like decreasing loss or anything through time. So I don't think this is overfit. So initially, the first thing we tried, the first approach was something like this, where try to just outline the dark patches on this map. And that that was the input data for the model, and then trained this Unet, and then that spit out the polygons themselves and an edge, and then I used object labeling to separate the polygons. And so this was an early output. It doesn't look horrible. Obviously, it misses a lot of polygons if you zoom in. So it's missing all these polygons here and there, but I just didn't like the accuracy wasn't very good, like what's going on here and what's going on there. I wasn't super excited, so I wanted something better. So in the next series of images, I'm going to show steps through, try to steps through this fairly complicated process that we landed on. So here is part of a much bigger image that I used in this case, both in training and prediction. So here is one of those beautiful meanders. And then instead of trying to draw polygons for the training and having to think all the time, like where exactly is the boundary, right? Especially when you go from very dark squares or polygons to ones that are not as well defined. Instead of trying to do that, we decided to go for something like this. So first I draw these radial lines, just really beautiful regular pattern showing how the band was expanding through time. And then, so these are very continuous. Like this is a repeated thing, that these radial lines are very continuous, and you start inserting new ones. I mean, not you, but the point bar nature starts inserting new radial lines when the distance between two exceeds a threshold due to meander expansion, right? And then in between those, there are more discontinuous scroll parallel lines like these. So we do this in QGIS, and then you can use polygonization to convert these into polygons. So that's the output of that. If I take away the initial lines, that's how it looks like. So this is my training data. And what I want to do is to generate with the Unet a 3-class image where I have the core of the polygon, I have the boundaries, and the background, everything else, right? So that's the target, that's the output. And here is only the edge of the boundary, the boundaries of the polygons from that Unet output superimposed on my original image, right? So this is the output. And I think it, it doesn't work everywhere, but in this setting for this river, for sure, I think it works pretty well. And then in the next step, I said, okay, we can convert the cores, what were the polygons in the Unet segmentation. I can just use object labeling, simple image processing technique to create these polygons. And this is not bad. I kind of like it. The problem is that why, I'm using a certain width here for the boundaries, and so that's kind of arbitrary. Again, I'm facing the problem that the polygon size and the gap between them, it's a little bit up to me how I decide to do that, right? So I wanted to get rid of that subjective piece. And the way to get rid of that is you say, I'm actually gonna map the boundaries. So here I have my Unet output, and then I convert that into I actually use skeletonization. I'm skipping some steps here. Use skeletonization on that, convert the skeleton into a graph, and then I convert the graph into polygons. And now these are my polygons. The boundaries are single lines. And as to me, that seems, for this particular purpose anyway, that seems like a very good approach. So I can take away the Unet output now, and this is my result in QGIS. So those are individual polygons. I can also make a graph out of this and store it that way. I call that a primal graph. Some of this is inspired by work done by urban geographers. Very interesting and useful stuff. And then if I put back my manual training data, you can see that it's not perfect, and I didn't actually compute an accuracy here, but I'm happy with it overall. And then I can also, again, inspired by what geographers do, you can create a so-called Rook neighborhood graph from so these polygons are connected to each other. Some of them are connected to some others, and you can map those connections by putting another graph on top of this, and I call that a Rook graph, which is the red lines. And I haven't done much with this yet, but the idea is that these radial lines that I'm showing here in black, now these are connecting the centroids of the polygons, right? So those are different radial lines than the first ones I showed, because these are connecting the polygons themselves. So these radial lines are actually part of this graph, this Rook graph. So I'm hoping to be able to extract information like that. So again, this is not big data, this is small data. This is the map we have done, at least I have done so far. So most of these polygons along this river, if we zoom in a little bit more, you can see that despite the fact that my model was not trained on non-point bar polygons, it does a decent job in places where they are pretty well defined. And you can see here how different these polygons are. There's no preferential orientation. That would be nice to be quantified, but I didn't get to that point yet, compared to the point bar polygons, which are very organized, and there's definitely not isotropic. And if you zoom in, just let me show you a few more images with details. So here is the more conventional iso-edge polygon pattern, and here is the graph, the network that comes out of my processing pipeline. And again, remember I have no training data that would use images like this, yet it does an okay-ish job. Obviously, it's missing some polygons. The model doesn't do a good job at all with this kind of pattern. So my thoughts on this is that I think the model is good enough that we could generate more training data and make the model more general than it is right now. If we look at another set of point bars, this is the network output from that. Again, overall, not too bad. Here is a beautiful big point bar further closer to the sea, so it's larger, the river is a little bit wider, and look at those patterns, just really, really nicely reflecting how that point bar has grown through time. And if we can zoom in a little bit further to give you an idea how it looks like. So that's the image. This is the graph, you can view it as a graph or just the polygons that are touching each other. Both representations are easy to generate. And then here I'm switching back and forth between the Rook graph and the primal graph. So this is the primal graph, and this is the Rook graph. And then, so I'm not super familiar with the literature on iso-edge polygons, but I haven't seen papers that would do this kind of, graph representation extracted from imagery, as opposed to digital elevation models. So this is a nice paper, actually. This is by a group at UT, Michael Young and his former PhD student, where they extracted polygon boundaries from LiDAR data. And it looks like I have a few more minutes left. So in parallel with this work, we kept doing the work on meanders, and so Cole has been working on me on this with me on this for a while, and we had this approach called dynamic time warping. We used it for mapping river migration, basically bank and centerline migration, and he was not very happy the way some of these things worked. So we came up with the idea that if we sampled these channel lines with very high resolution and then use this dynamic time warping, we could get a lot better results. So that's how this kind of tracking / modeling was born. And at the same time, I was looking at these polygons, and the idea came that if we start tracking these radial lines, at one point we can add these secondary radial lines, just like in the permafrost polygons, where when this distance exceeds the critical threshold, then I insert a new starting point, and then I keep it tracking. And here the colors are migration rates. So you have large migration rates where it's yellow, and low migration rates where it's blue. And this is a numerical model, but there are many similarities in the overall patterns that you see here with the meanders that we see in Siberia. So that's super interesting as well. And so here are some images showing how you go from, these are the model center lines, and then you add these radial lines, and then you can convert that into point bars themselves and paint, in this case, the migration rate on those point bars. And the idea, of course, is that we can do this with actual data as well. I'm just not going to show that here. Instead, I'm going to show an animation where, again, colors are migration rate. You can see how those radial lines show up in larger numbers as you are expanding the meanders. Yeah, that's basically it. Some of the key points, I guess. Ice wedge polygon development on point bars can result in highly regular patterns that record channel migration if the migration is slow but constant through time. And you know, there should be some small print here that this is a hypothesis. Training a Unet on a polygon network gave better results than training it on polygons. Working with graphs, and I'm using a Python package called networkx, seems promising for both mapping and analyzing the results. Only tested the model on a limited area, and proper high-resolution imagery is needed to take this any further. Likely more training data is needed, but I think this could be sped up. Instead of doing a lot of manual work, this could be sped up with the existing model. And obviously, I'm here to get in touch with you all, and I'm happy to talk about collaboration if there is any interest, or if you know, happy to receive any feedback you have. Thank you.